So the hardest math problems of 2020 is definitely a clickbaity title. By the hardest math problems, I don't mean problems in all of mathematics in the year 2020, because that would include the Millennium Prize problems like the Riemann hypothesis or solving the Navier-Stokes equations. So those are hard problems, perhaps impossible to solve. What I mean by the hardest math problems is this set of problems. It's this year's Schweitzer problems. So the Schweitzer competition is a math competition in Hungary, in which 10 or so problems are set by Hungarian mathematicians, and undergraduates have 10 days to look at these problems, try to solve them, try to solve as many as they can. And they are generally considered to be really hard problems. So students are allowed to use basically anything, any books, research papers, the internet, except they are not allowed to talk to each other and collaborate because it's a competition. But of course, that means they have to do some really deep thinking and individual hard work. And after the competition, we are free to discuss these problems. So I had the idea that since these problems have been posted on the competition's website in English, I will include a link in the video description. We might want to look at these problems. Now the solutions have also been posted on the website, but only in Hungarian. So I figured the intersection of math people and people speaking Hungarian is fairly small. So I wanted to look at these solutions, understand them, digest them, sort of try to formulate them in my own way and share them with you, so it reaches a wider audience perhaps this way. Let's look at the first problem, which should appear on the screen now. It deals with sequences of natural numbers, and it starts with a definition. Basically, it tells you that two sequences, x and y, of natural numbers are completely different if they don't match at any point. So if if the nth term of x and the nth term of y is not equal for all indices n. Okay, so this is just a definition when we say that two sequences are completely different. So this is an important part of the problem. And then we are asked to consider functions which take sequences and assign natural numbers to sequences of natural numbers. So for each sequence x, we assign a natural number f of x, is a function with the properties so it has some special properties, this function. The first one is that completely different sequences get different numbers assigned to them. So if x and y are completely different, then f of x is not equal to f of y. So that's the first property this function has. And the second property is constant sequences. So a sequence consisting of only the numbers k would get that number assigned to them k. So this happens for all numbers k. Okay, and the problem is to prove that there exists a universal index such that f of x is equal to x of n for all sequences, for all x. So what it means that there is this universal index, this place in each sequence, and it's the same place for all sequences, where if you look, you will find the value of f attached, assigned to that sequence. So it could be 10, and that would mean that f, the value of f for each sequence can be found in the 10th place, 10th term in the sequences. Okay, so this universal index, of course, could depend on our choice of f, but here we assume that f is some arbitrary function with these properties. So, and we should prove that there exists such an index for each of these functions. Okay, so if you want to think about these problems and try to solve them on your own, that's completely fine. That's great. Feel free to pause the video at any point. I will give you hints throughout the proof, and you can pause the video at any time and try and see if you can continue with the solution. All right. So the first thing that we should notice, or perhaps suspect, is that for such a function, it will be true that no matter what sequence we look at, the value assigned to that sequence will appear in the sequence itself. Okay, let me formulate this as a lemma, because we'll use this statement later on. So for any sequence x, we have the following. It's the value that f assigns to x should appear in the list of numbers consisting, making up x. Okay, so this is our statement. For any sequence, f of x is an element of the set of numbers making up x. So we will prove this by contradiction, so it's going to be an indirect proof. Let's just think what it would mean if f wouldn't be, f of x wouldn't be an element in x, in the sequence x. Well, then x, so f of x wouldn't appear anywhere in the sequence. That would mean that x and the constant sequence made up from f of x would be completely different, because nowhere in the sequence x would f of x appear, right? So that's what it means. That is exactly what we mean by completely different sequences. So x and f of x are completely different. Okay, but that means that f should assign different values to these completely different sequences. So f of x, so the value assigned to x, would be different, not equal to the value defined, assigned to this sequence consisting only of f of x. Okay, and what is that value? Well, for constant sequences, f assigns to that constant from which that sequence is made from, so that's f of x. So here we have just shown that f of x is not equal to f of x. So that's a contradiction, and so the lemma is must be true. So we prove the lemma. We now see that for such functions, the value assigned to each sequence should appear in the sequence. Okay, so next we should look at, let's just look at some special sequences first and try to see if we can build up the proof of the original statement from that. So now we know that there are, for each sequence, there is at least one index where we find f of x in the sequence, but we have to prove that this is a universal index, so that there is a unique index that, well, at least one index for which all sequences are such that f of x is equal to the nth term of the sequence. So let's look at some special sequences. So let me go on to move on to the proof of our original statement. So we will take probably 4 steps to get to the end, but these steps are small enough so you can always pause the video and see if you can continue, try to finish the proof from there. So first, evaluate f on the sequence of natural numbers, okay? So evaluate f on, let's denote this sequence of natural numbers by e. So it's just the sequence of natural numbers, and of course this is, at least, well, if you didn't believe this lemma, now we've proved it, this sequence would definitely be a sequence for which you would believe that whatever natural number f assigns to it, it should appear in the sequence somewhere, okay? So it's definitely true that f of e is equal to some term in the sequence, so the nth term in the sequence, which is exactly n, for some n, okay? So for some index n. So that's the point. We look in the sequence of natural numbers and find the value which f assigns to this sequence. So that could be the nth term, which is n exactly. And then next we could, so if this statement, if we want to prove this statement, that would mean that we should, well, this n, this special n, would definitely be our candidate for an index for which this statement holds true. So let's just try to consider slightly more complicated sequences than this one or the constant sequence, for which we give a special meaning to this nth position. So a slightly a slightly more complicated sequence than a constant sequence would be the following. So for sequences of the following form, let's call these sequences XA. So the way I'm going to build up these sequences, I'm going to have it almost a constant sequence, but I will change it at the nth term and the nth place. Okay, so that's the nth place is equal to, it's equal to A. Okay, so for these sequences, the value that f assigns to it should be either n or a because of our lemma. So we would have f of xa being one of two possibilities, n or a. Okay, but notice that xa and e are completely different because e has E is the sequence of natural numbers, and none of these none of these numbers are in the correct place. So, and in the nth place we actually put something else than n, perhaps. So they are completely different. So E and xa, if a is not equal to n, are completely different. Which means that f should assign different values to e and xa. So f, remember, assigns the value n, this special value n, to the sequence e. So it shouldn't be assigning n to this sequence xa as well. It should assign a instead. So implying that f of xa is equal to a. And that's actually true for all natural numbers a, including n, because if a is equal to n, then we have the constant sequence consisting of only n, to which f would assign the number n. Okay, but the point is that for these special formed sequences, f assigns that number a at the nth place. So it's actually true that for these sequences as well, that f will assign the value which appears in the nth place in the sequence. Okay, so now we looked at sequences that are almost constant except for one place. Now we'll do the opposite. We'll go to the other extreme. We are going to look at sequences which for which none of these terms are equal to n. Okay, none of these terms which are not the nth term are equal to n, and we look at those kinds of sequences. So any such sequence y with the property of the mth term not being equal to n, if the place we are looking at, it's not the nth place itself. So for these sequences, we have they are completely different than xa. Okay, so let's see. I'm saying that this sequence, so this type of sequence, is completely different from xa for all a except a equals y of n. Okay, so if you look at these types of sequences for which none of these terms are equal to n, none of its terms are equal to n, when we are looking at the terms that are not the nth term, they will not coincide with they will be completely different from xa, as long as we, at the nth place as well, we have something that is different from the nth term in the sequence y, okay? So the function f should assign different values to x, a, and y, because they are completely different, okay? So that of course means that if we go through the natural numbers with a, we will exclude, well, of course, we know now that f of xa is a. So as we go through the natural numbers, we will exclude every one of them except each and every one of them except except yn. Okay, so this means that they are completely different, that should assign different values, that f of y should also be yn. Okay, so it cannot be any of these a's where a is different from y of n, so it must be y of n. And finally, if we look at any sequence, so for any sequence z, we define a sequence like the one in the previous point. We will call this y zb, let's say, and let's define it by having its nth term be the natural number b, which should be different, which should be not equal to the nth term of z. Okay, and the rest of the terms of y zb should be taking the corresponding term in z, then adding n to it. N was that special index that was assigned to the sequence of natural numbers. So this is how we define this sequence y of yzb. So if we define this sequence like so, we see that the terms in the sequence yzb are all different from n, because we are adding some natural number to n, and in this problem the set of natural numbers starts with 1, so they are definitely different from n because they're all strictly greater than n. So they satisfy this condition, and they are completely different from all xa's if a is not equal to y zbn, which is b. So the point is that now we can just simply apply what we have learned in the previous points. So to consider the value assigned to z, well, it's completely different. So from z is completely different from yzb. That's very important. So all of these corresponding terms are different numbers. So it's not equal to f of yzb, but f of yzb is a sequence of the type that we see in points 3. So to that sequence, these types of sequences, we already established that it will assign the nth term, which we defined called b. Okay, so f of z cannot be b equal to b, and b was an arbitrary natural number chosen to be different than the nth term of z. So we can exclude for f of z, we can exclude for its values all of the natural numbers except z of n, meaning that for an arbitrary sequence, z, f of z will be the nth term of the sequence. Okay, and this concludes the proof. Again, in this proof, you have seen that there exists a universal index, such that if you look at those places in every sequence of natural numbers, it will be the value of f assigned to that sequence at that place. And we actually, in the proof, found that that place should be the place where the sequence of natural numbers is mapped by f. So exactly that value, that index should be f of e, where e is the sequence of natural numbers. Okay, so I hope you like this video, and let me know which problem would you like me to look at next. See you next time.